So last time I talked a little bit about we call the definable Gaga theorems, sort of a non-compact version of some classical comparison theorems between the algebraic and the analytic category. The definable world exists more generally without the compactness assumption. And today I want to prove that. I want to use that to talk about some more algebraization theorems, how they sort of exist in a definable world, and how they can be applied to Hodge theory. So let's just start with the classical case. The analytic world. What does the picture sort of look like? Well, one basic question you can ask is the following. You can take X to be, let's say, compact for now. Complex space. You can take it smooth or reduced or whatever else it is that you prefer. You can ask, when is X algebraic? By which we mean when does X admit the structure of an algebraic space, which when you analytify, you get X back. Note that because we're in the compact case, because of Gaga, there's not a concern for having more than one algebraic structure. If you have two algebraic structures, then you have an analytic isomorphism between them, which would have to be an algebraic isomorphism by Gaga. So this is sort of a well-defined question without much ambiguity to it. So the answer looks roughly like the following. If the dimension of X is 1, then the answer is always. This is basically due to the work of Riemann. This is so-called Riemann existence theorem. With every compact Riemann surface has global meromorphic functions on it, which you can use to give it an algebraic structure. And the dimension of X is bigger than 1, the answer is usually not. You can say more, of course. But as an example of this usually not, if you let L in C squared, or just C to the n even, be a lattice, so discrete and co-compact, so just some z to the 2n sitting inside c to the n, not contained in the proper real vector space. And you even look at c to the n mod L, you get this sort of complex torus. Most of the time, this is usually not algebraic. Unless L admits a certain form. Okay, so once algebraic, give the structure of an algebraic group with a bigger variety. If n is bigger than 1, most of the time it's not algebraic. And you can make various other examples as well. Okay, so when do we expect algebraic structure? This was answered by the work of several people. Well, one of the easiest properties to get a handle on when you do have an algebraic structure is you have a lot of rational functions on you. Because you have affine open sets, they will have regular functions on them, and those will become globally rational. So in particular, globally meromorphic from an analytic perspective. So given an X, we say that X is Morrison if that for sentence degree of M of X, where this is the field of meromorphic functions, is equal to the dimension of X. Now note that if we replace this equal to by a less than or equal to, this is always true, that's not obvious. But I believe a theorem of motion is on. I couldn't find exactly what this is.
What did you say about less than or equal to?
So this is always true for any
less than
compact analytic space. Yeah. And if it's as big as possible, then we say it's smushed. Okay. This is certainly a necessary criterion for X to be in an algebraic space. And Tsimerman's theorem. In fact, all compact Moissan spaces are algebraic. Now, this doesn't, I mean, in some sense, it's a satisfying answer. Of course, given a compact analytic space, it's in general tricky to look at it and answer whether it's Moissan. So it's maybe not it's not as complete of an answer as you might want, but it's you know, it's pretty good.
Does the proof of this use the Artin approximation?
Yeah, that's right. So we'll talk a little bit about that. The proof of that definitely uses Artin's work in formal spaces and Artin approximation. Absolutely. In fact, I want to give an idea of the proof. Point out kind of things he does. So the idea is basically as follows. Suppose that X is Moissan, so it has a bunch of these functions. So pick some functions, F1 from F dimension of X, which are meromorphic on X, which are algebraically independent. And suppose the Fi are all regular on U. You have holomorphic function, or I should say holomorphic, not big. We're in the analytic category. On U and X, which is the Zariski. So U is the complement of some proper complex analytic subvariety of lower dimension, along which the Fi's maybe have some poles, but they're holomorphic on this open set. Then what we can do is we can look at gamma S of F, the graph of F, inside X cross, let me call it, I guess, C to the power of the dimension X. We can embed this further inside a compact space, X cross projective space, dimension of X. It doesn't really matter what you put here. We can compactify in other ways. There's nothing subtle going on with this particular compactification in this case. So then the idea is to consider the closure gamma F bar. Inside of this academic function. Now note that if you look at this closure and you look at the pre-image over X, so the pre-image of U over X, you just get gamma F back. No reason to add anything in the closure over U, it's already the graph of something, it's already closed, it's already nice. The closure only gets sort of, I shouldn't say weird, but mysterious over the complement of U. Then you might get components of more dimension than you expect, and it's kind of hard to say what it looks like. Nonetheless, it's some analytic space. And you have this picture where there's a little bit more room. If you look at this closure, on the one hand, maps down to this projective space. So this is pi2, this is pi1. On the other hand, it maps down to x. And we have the properties that pi1 and pi2, first of all, are proper, because everything involved is a compact space. There's no escaping to infinity anywhere here. Secondly, this pi1 and pi2 are generically finite. In fact, pi1 is generically an isomorphism, which is the modification here. And the third property is kind of obvious, but I'll say it anyways, is that this space here is algebraic. It's just projective space. Okay, nothing deep there. And so then step one is to deduce gamma f bar is algebraic using pi2. You show that any finite cover like this of an algebraic space has to be algebraic itself, any generic and finite cover. And then step two, unsurprisingly, is to deduce X is algebraic. Using pi1. So the idea is you relate compact analytic spaces to each other using these kind of maps, which we'll talk about more in a second. And you show that you can both go up in terms of an algebraic structure, and you also come down. Okay. So that's how the proof goes, very, very loosely. So we're reduced to understanding what happens along such maps. So here is sort of one key definition that's involved, made by Artin. What he calls a modification. A modification is a map phi from x prime to x, which is proper Proper is important in all this stuff. If it's not proper, it's kind of very hard to control anything. Such that generically, this is an isomorphism, and then on some closed subset, it does something interesting by blowing things down. So it's a modification, so that you have this kind of map, such that we can write X as some open set U union some closed set Y, where U is the risky open and Y is the risky closed. And look at the map from phi inverse y, sorry, from phi inverse u, this is an isomorphism. Okay, these are the simplest kinds of maps that you can sort of study in higher dimensions, these kind of proper maps. And they're called modifications because essentially generically nothing gets touched, but then there is some Zariski closed set, which is blown down in a significant way. This map here is not finite. So if you look at the map from phi inverse y to y, this map is proper, but nothing else. So for example, we could blow down dimensions. So a typical example of this is if x prime is the blow up along some closed set y of x. So you pick like a point inside a surface, for example, you replace that point with a P1 while directions approaching it. Then away from that point, nothing's happening, but at that point, you replace it with a P1. Okay, so this makes sense. In both algebraic and analytic categories. You have this notion of a modification in both worlds. And now Arden, to prove his theorem, essentially has to show the key step is sort of compare algebraic structures along modifications between compact, complex, analytic spaces. Because this, yeah.
I have a question about this too. So where did we actually use that we have dimension of x theoremorphic functions?
Oh, just to give this many functions to begin with.
Yeah, did we use somewhere in the proof?
Yeah, absolutely. Because we need the map pi2 to be generically finite.
Oh, yeah.
Because otherwise, there's not enough information recorded about this from this. So, like, if you have no functions, this is just x again. You're mapping to a point, and you're learning very little.
So the image of pi2 is all of this, all of the whole projected space.
Pi2 is surjective.
Yeah,
That's right. Absolutely. Has to be. Other questions? So essentially, pi1, I mean, pi1 straight up is a modification by construction. Pi2 is not, it's generically finite, but that's very, very mild. Finite maps are very easy to understand. Replacing finite with isomorphism is easy, relatively speaking. The harder part to deal with is this, is sort of messing things up by changing dimensions. Other questions? Okay, so what sort of is happening here in Arden's setup? Let's talk about the harder part. It's more relevant for us anyways, which is step 2, this sort of going down. Let's say we've algebraized gamma bar, and we want to algebraize x. And let's think about it in that setup. So gamma bar is algebraic, and we have this decomposition into U union Y. And now by induction, we can assume that Y is algebraic, because Y is a subspace of X. Subspaces of Murchison spaces are Murchison, that's not hard to show. And U is algebraic because U lives up here, and anything inside an algebraic space is algebraic. So what we want to do, the sort of goal, is to define an algebraic structure on X by gluing the structures on U and Y. That's kind of the idea. But you can't just do it if you if you just look at the point sets, because what you're missing is the gluing information between U and Y. It's not just that you have these two sets and they put together. You have a lot more information in how they would glue together. And the idea is to record that information, as we've been talking about before, by looking at infinitesimal structures. So not only do you have an algebraic structure on Y, but you can thicken Y and get more and more algebraic information. And the idea is if you have all of that information, that's in fact enough to glue the algebraic structures together. So let me say a little bit more about that. And this is where the motivation for all this important stuff we've been doing comes from, essentially, or came from for us. So, suppose that Y is defined by the ideal sheaf, IY, yeah. On X, so IY is the sheaf of functions vanishing on Y. You can imagine Y just defined by some function, the ideal derivative of functions. Then what we can do is for every integer k, we can define the kth thickening of Y, kth infinitesimal thickening by the vanishing not of IY, but of IY to the power of k, of k or k plus 1, that's how I index it. Let's say if k plus 1, that's how I use it. So y sub 0 is equal to y, and then y sub 1 is IY squared, and the idea is that it gives you tangent information, then you keep going, you get more and more infinitesimal information. The idea is if you know Y is algebraic, but you don't yet know X is algebraic, moving to X, you have no sort of algebraic control over what happens. You fully enter the analytic category. But if you look at these infinitesimal thickenings, a priori they're defined analytically, but at least they live on an algebraic space Y. And so now you can study sort of Y, which you know is algebraic, to try and get some kind of handle. So these are more accessible than just moving to X right away. Sort of want to slowly crawl out to X using these thickenings. So then you put them together by defining X sub Y to be the formal completion of X log Y. So you can write X and Y as the limit in an appropriate category of all of these Y sub k. So consider the whole formal neighborhood as one. Just to give an example of what this looks like. We have two examples, one sort of more straightforward, the other one a little bit trickier. So if X is affine space, Y is a point, 0, then IY is just the ideal generated by a coordinate here, let's say T. Y sub k, you can think of a spec of C adjoint T mod T to the k plus 1. So we have up to order k infinitesimal information. And x sub y is just, well, spoof or whatever, but it corresponds to C power series adjoint, sorry, Alex. So you get this power series ring. And so you already see here, even in this simple case, the phenomenon that even though y is a closed subvariety of x, if we put together all the infinitesimal thickenings of y, we in some sense get something bigger than x, in which we can see x. The second case, I'll say x is a squared. Let's say spec of C adjoin two variables, s and t. And we'll let y be the vanishing locus of s. So it's the t-axis. Then y sub k is very similar. It's spec C adjoin t comma s mod s to the k plus 1. So arbitrary polynomials in t and order k polynomials in s. So at every point on the t-axis, we're reporting sort of k directions along that line. And if we look at x sub y, we get a ring which is slightly more complicated than what you might expect, maybe not. But you look at C polynomials in T, and then this whole ring, power series S. So I'm not going to focus on the technicalities, but this is a different ring than C power series S and then polynomials T, and that kind of stuff ends up mattering quite a bit here. Regardless, you get something which is bigger than x, in which you can see x. And somehow the idea, Artin's idea, is that if you record not only u and y, but if you record the completion of x along y, and somehow a way in which u sits inside that, that should be enough to study all of x. So that's enough to sort of glue x together from these two pieces.
We always have this sort of thing, x, y.
Basically, yeah. Because the idea is that if you have a function which vanishes not only on y, but on y to all orders, then its germ has to be 0, and so it has to be 0 because it's holomorphic. So you always have an embedding of the functions on x into formal functions on x sub y. Just kind of like how you can read off any functions from its germ at a point. That's what's happening here. But x sub y should be thought of as like, it's still a very small neighborhood, like it's still only giving you the germ. So it's hard to read off informations on x from functions here. Because given a formal function here, you can't like evaluate at some other point, just a formal function, you don't know if it converges. Still, you can kind of see x inside there. Cool, so then what Artin does is he says the following theorem. So suppose x prime is algebraic. And you have a map from the analytic space corresponding to x prime to some other analytic space x, which is a modification. We don't a priori know x is algebraic, x is an analytic space. And suppose that phi inverse U maps isomorphically to U, and phi inverse root U, and let the Z be phi inverse Y for our decomposition of X into U union Y. Now we're going to suppose the following thing. Suppose Y can be algebraized as Y naught. And moreover, you can't just algebraize Y, but you can algebraize the entire formal neighborhood. So all the infinitesimal segments. X sub Y can be algebraized as some algebraic space, formal algebraic space, X sub Y naught. Right. Then X and phi can also be algebraized. You don't really need the maps, the spaces to be compact. You just need the map to be proper for his theorem to work. But yeah, so Arden says, suppose you want to descend the algebraic structure from some analytic space to some other one along the modification. Well, along your open set, there's nothing to be done. You're already algebraic, so job. Along the complement, then you have to do a bunch of work, but of course it's easier because dimension is lower, so you can kind of have already done that work in some sense. But you have to algebraize your entire map on Y from its inverse image Z. And oh, sorry. Suppose Y can be algebraized, so this is true, and this is true, and this map from X, let me write it down here. Apologize, I missed something. Or maybe it's implicit, but I want to write it down explicitly anyways. Suppose you can algebraize Y and its formal completion such that the map phi from X prime sub Y prime, sub Z, I call this Z, and a limified mapping to X sub Y is also algebraic. So it's not enough to algebraize the bottom, it's algebraize it in a way that's compatible with the algebraic structure at the top at every infinitesimal level. So if you can algebraize the formal completion, then you can actually glue that and descend to a full algebraic structure. Okay. And using this result, Arden proves his theorem that compact dimensional spaces are all algebraic. Okay, so this is kind of how the classical picture looks like. So the idea is going to be that this all jives very well with the definable picture, because now what we have to do is algebraize these infinitesimal neighborhoods of these Y's. And because everything's definable, we have sort of non-compact Gaga theorems and Chow theorems. It should all be free as long as you have some nilpotent information that's allowed. Okay, let me move to the definable picture. Turns out you have some very general results in the definable world. To state them, let me first make one definition. We're going to be talking about images of maps between algebraic varieties. So we need some notion of an image or surjectivity. So we say a map between two spaces is dominant if, I'll write it this way, the sheaf of functions here mapping to the push forward of the sheaf of functions here is injective. A fancy way of saying a function here can't pull back to 0 without being 0 itself. So note that if you're proper and dominant, then you're surjective. Although surjective doesn't imply dominant, and you need the proper. So just a couple of examples. It's a bad idea. We go on keyboard. As a couple of examples, simple examples. So first of all, any open inclusion like C into P1 is dominant but not surjective. Because you can't vanish on C without vanishing on all P1, it's holomorphic. And as a second example, in for example, any of those cases, the map from something to its infinitesimal thickening is technically surjective on points. Adding the potence doesn't change your point set, but it's not dominant. The whole point of doing this is you do have functions which are sort of 0 everywhere, but are not 0, they're nilpotent. So it's kind of a complementary notion. Okay. So I want to mention the following algebraization theorem, which is kind of clean and doesn't talk about Hodge theory at all. It's the generality of definable analytic spaces, but applies to it very cleanly. So suppose we have some algebraic space X, could be an algebraic variety if you prefer, and S would be a definable analytic space. With a priori no algebraic data at all. And we have a map phi. Now I'm going to be slightly careful to specify which category we're working with. So phi is a map from the definabilization of X. So we think of X as a definable analytic space to S, which I'm going to assume is topologically proper. You probably shouldn't need this assumption, we think, but we can't make the proofs work without it. It's kind of harmless, and so we have it in. It's presumably not really necessary, but that's what we have so far. Then there exists an algebraic space Y and the map F from X to Y, which is dominant. Such that you have the following diagram. Here you have the map you started out with, phi. here you have the definabilization of f, the definabilization of y, and here you have this map I such that I is a closed emergence. Okay, so you have this arbitrary map from an algebraic space to a definable analytic space, which is proper. And you can factor that as sort of a surjection, this proper dominant map, followed by this inclusion. So in a sense, we can say that y here is the image of this map phi. Okay, so one can say, can summarize this theorem as saying that definable images of algebraic spaces are algebraic. So what's interesting about this theorem, perhaps, is that S has nothing algebraic going on except for this map from phi. Of course, if S was algebraic, this is a definable map, this would just be some version of definable Chow or definable Gaga or something. As long as you're definable and inside something algebraic, you have to be algebraic as well. The whole point of this theorem is you're not inside something algebraic, you're inside something that's purely definable. All you have going for you is that your source is algebraic.
Well, the map phi should be definable, right?
Yeah, so it's a map between two definable analytic spaces.
Oh, yeah, okay.
Absolutely. Absolutely. And of course, this y and this x to y are unique up to isomorphism. That's all easy. Questions about the statement? Questions? Cool. So, as an immediate corollary, after all the work we've done on Hodge theory and period maps, if you have a period map to one of our D mod Z's, then phi of x is in fact algebraic. We have a definable structure here. We've shown that f is definable, and so the theorem directly applies.
This is new.
Oh yeah, so this is the Griffiths conjecture.
Oh,
This is exactly what Griffiths conjecture. There was previous work in special cases, when things were smooth or compact or whatever. But in general, this is new. I don't mean or whatever derogatory. There's a lot of important previous work on this. I just think there are a lot of cases. So yeah, so just to give a brief history of this. In the case where X is compact, this is due to Griffiths, which led him to make the conjecture. And his main observation was that this follows from the Kähler embedding theorem. Because there's a certain line bundle you can just write down using the Hodge theory, which is going to give you, which is going to become positive and integral on X. And just using the differential geometry, you can show that that gives you a projective embedding. So if you're compact, you sort of have your projective space. You're mapped to projective space immediately, and that means you're algebraic. The subtlety, though, is when in this approach is when you're not compact, and then you're not sure what happens at infinity.
Just my question. When we define a period map, we start with suppose that X was
Yeah. So X is well, not projected, but X should be algebraic for sure. X is algebraic, yeah.
not projected. It's not
It doesn't have to be projective. No.
Yeah. The first class.
No. So in the first class, what we were dealing with were period maps coming from projective families over X. So we had like a space Y over X, for example. We looked at the cohomology over fibers, and we used that to give a period map. But you can have a family of projective varieties over a non-projective base. Yeah. So the base can be arbitrary. So this approach of Griffiths is still central, I want to say, to this whole story, and it's kind of funny. So the way it works, you first prove this is algebraic, so it might be some algebraic space, this messy category I introduced earlier. But once you have that, you can use this observation, this work of Griffiths, and some other arguments to show that in fact, phi of X is actually quasi-projective. Quasi here just means it's not a closed subvariety of projective space, but it is a subvariety of projective space. So after the fact, you can actually show this.
This is in the still in the compact case or in the
No. This is in general.
oh
Yeah, this is in general. No, in the compact case, it's in fact projective.
oh yeah, of course it is compact
By the
itself.
exactly. But in general, you have this. And one other thing I want to mention is that so this theorem, I mean, the way it's phrased here, cares very much about all the infinitesimal structure. It's not just that we're looking at the image of X, but because we have this dominant condition, which we defined there, we're in fact like recording the entire infinitesimal structure of the image of X. But you might be like, well, I don't care about that. Suppose I only care about, the reduced space, no nilpotents, just the image, can I algebraize it? And maybe the answer is yes, but because of the approach we're taking, which we'll talk about after the break, with this sort of deformation theory, even if you only care about the basic result, you need to keep track of all this nilpotent data for the argument to work. Okay, why don't we take a 10-minute break and then talk a bit about the proof.
I didn't move around too much. I've never figured it. No worries, no. If anything's pretty good actually.
Yeah, okay.
Everything was now active and interesting.
So there you go.
Fine.
Okay.
So,
oh, did you see the stuff people the interview for the
Oh yeah. Yes.
where I was wondering whether you know in advance. I didn't.
Yeah. Well, I did know that Slavek was being looked at.
Yes, okay, good.
And
would
that
be-
he applied.
Yes, that would be an elegant solution,
Yeah,
right?
yeah, that would be ideal if it would work out.
I was surprised. I just saw the email yesterday and I didn't know anything.
Yeah, no, I was aware of it. Okay. I hope it will work.
Yeah, me too.
Oh, yeah, okay, yeah.
Um, let's continue. So, okay, let's, I want to say something about the proof of this theorem. So there are basically three kinds of arguments we need to prove this theorem. And three arguments are as follows. So first argument is reduce to the case of modifications, phi being a modification. Because a priori, to begin with, this map phi could contract dimensions quite strongly, and then it's not at all obvious what's sort of happening in the base. When you contract dimensions, your algebraic structure, in principle, gets lost. The second argument, the second kind of argument, is you want to extend algebraic structure that you have on the image over thickenings. So at various points in the argument, you have an algebraic structure over something in X, something in S, and you want to extend it to a nilpotent thickening of that thing inside of S. And finally, once we have these two ingredients, eventually what this is all leading up to is to apply Arden's result. Result on formal modifications. This thing over here. So eventually our goal literally is going to be to apply this theorem where we have some algebraic structure for some open set. By induction, we have it on the complement and all of its thickenings that will glue it for us and give us the algebraic structure on the entire F. Okay, so loosely, these three sort of arguments are what put together proof, or not even that loosely, pretty strongly. And one thing we have going for us is that X is algebraic, even though S is not. So anything pulled back to X automatically becomes algebraic as well. Because we're in a definable world, things are definable and analytic, and sitting inside something algebraic have to be algebraic. So let me say something about one. So again, a priori, the idea is that this map phi contracts dimensions, and we want to handle that. So let's focus on the case that X and S are reduced, no nilpotents, just so we don't worry about that headache for now. But dimension X maybe is very large. Or more relevantly, the map phi contracts dimension, the fiber is very big. Okay. So in this case, we use an argument that's pretty common in algebraic geometry. And the idea is the following. So consider for S in the image of X. It's not definable, but it's not algebraic, but it's some definable thing. For S in the image of S, consider X sub S, which is the inverse image of little s. This is some definable analytic subspace of X. And so X sub S is algebraic by definable Chow input. This type of contracting is algebraic. However, it varies definably in S. And so as a consequence, you can deduce that for a Zariski open U inside the image of X, X sub S looks the same as S varies in U. So essentially, maybe it's usually 2 points and sometimes becomes a point. Or maybe it usually looks like a smooth curve of genus 2, but sometimes becomes a curve of genus 1 or something higher dimensional. But essentially, it usually looks the same, which means XS varies flatly over all S in U. Is a sort of formal way of saying it. And this is not something deep. This is just some definability, finitely many possibilities, all that kind of stuff. You just make the appropriate arguments and throw in definability and follow very quick. There's nothing deep right now. Okay, so now remember, our goal was to take our situation and reduce it to a situation of this case where the map phi is a modification, which basically just means that over an open subset of the base, the map phi is an isomorphism. That's over a Zariski open subset. That's our goal here. And our current situation is we have, let's say, here is S in the base. And you can imagine X looks something like this. So what we can do instead is, instead of X, we can consider, let's do a generic fiber here. What we can do is we consider the space of these pre-images instead. So each S here at the bottom, especially over U, gives us a cycle of a specific type. So now what we can do is we can let, I'll just call it Hilbert of X for Hilbert scheme, particular component of it. But what this is going to be the space of cycles on X of type X sub S, where S is in U. So of the same Hilbert polynomial, basically. But whatever, all cycles which look like the ones you get by taking the generic fiber of something S. Then this is algebraic by general nonsense about algebraic spaces. You can do this kind of construction and stay in the algebraic world. You can modulate, you can parameterize your algebraic subvarieties algebraically, and that's all that's happening here. And moreover, if X still has a map to S, you can show that these fibers, these cycles can't jump out across many different fibers. Since they started life over one fiber, they can't slowly move out. And this is a modification, well, is an isomorphism over here. Over you only have one such cycle, namely the pre-image of S itself. In general, you might have more, right? Like in our blow-up example, for example, if we're already a modification, we take a point downstairs. Generically, our pre-image is a point, but over the point we blew up, we have an entire P1. So if we do the construction in this case, we just recover X itself over here in the Hilbert space of a point. If instead you were to consider something which is generically a curve, like a family of elliptic curves, but over some point it becomes a surface, like a K3 surface or the Billion surface or whatever, then in fact your dimension here might jump a lot more. You only have one curve over most points, but over your bad point, you have to look at all curves that live within your surface. And that might be some high dimensional. So we have very little control over what happens over the like non-good locus, not what's in U, but over U, we have an isomorphism, and that's really all we care about. And so now, instead of studying the image of X, we can show that it's basically enough to study the image of this thing, and so you're down to the case of a modification. Okay.
Does this have the same image as the original tree?
Yes, you can set it up so that it has the same image, but you're right, you have to be careful about that. Absolutely. Essentially, the reason this is true is because there's like a standard way to compactify everything. So as long as you're good over Zariski open, you can set it up so that you're correct over the rest as well. But you're right, you have to worry about that. Okay. Okay, so that's step one. Now, once you're in a proper modification setup, then what's your setup? You've cut up X into something open, mapping isomorphically over the base, and something closed inside it, which maps in the proper way. So by induction, the closed thing you've already taken care of, if there's no nilpotent stuff. And then to apply Arden's theorem, what you need to do is to glue in all the nilpotent data. So that comes in the form of this following lemma, which is exactly about step 2, extending algebraic structures over infinitesimal thickenings. And that works as follows. So suppose you have the following situation. Suppose you have W maps to Z is algebraic. And let's stick to everything being proper. And now let's say W inside W prime is an infinitesimal thickening. So they have the same points here, but we're adding some nilpotent structure. But instead of considering an arbitrary infinitesimal thickening all at once, that becomes a bit unruly, we're going to consider adding one layer at a time. So instead of going straight from a point to the kth order neighborhood, we're going to go to the second order neighborhood, the third, and the fourth, and so forth. And in each step, what makes this nice is we can assume this is what's called a square zero thickening, which means that the ideal defining W inside W prime is square zero. The ideal x to the k inside Cx mod x to the k plus 1 is always square zero. So if you keep going one step at a time, you can assume this. And this is kind of nice. It lets you build up your form modification in these sort of small steps. So assume this. We have an algebraic thickening square zero of this. And we have a definable analytic thickening of Z. This is a indefinable category, and it's also an infinitesimal square zero thickening. Now, note that this might not be algebraic. There are, in fact, non-algebraic thickenings, just like there are non-algebraic line bundles that we talked about last lecture. And you can use those non-algebraic line bundles, in fact, to create non-algebraic thickenings. But this genuinely is a definable object. It's not sort of secretly algebraic. So suppose you have this kind of setup where you have an algebraic map, an algebraic thickening upstairs, and the definable thickening downstairs. And suppose you have, well, no, let me run it here. And suppose you have a map Phi prime from the definabilization of W prime to Z prime such that the square commutes. You have W maps to Z. I'm going to put everything in the definable category. Some things here are only definable. And I want this to commute. Okay? This is exactly the kind of setup that we have to deal with, only we've sort of zoomed in on the most essential case, which is we have a map. We've already algebraized it to some level. We have an infinitesimal thickening. And we want to algebraize the image inside the infinitesimal thickening of our thickening upstairs. What's the conclusion? Then there exists some algebraic map W to Z, W prime to Z double prime, and a map from the definabilization of Z double prime into Z prime, such that we have the following diagrams. So we can close this up algebraically, replacing Z prime by Z. Is this too small? Okay, by Z double prime. And we can fill in this map here by factoring it with this map. So W prime definabilized maps to Z double prime definabilized maps to Z prime. Essentially, we can break this square up into a smaller square and a triangle. Loosely speaking, what Z double prime is exactly the image of this definabilization inside of Z prime. So this is in the definable world. We can factor it all algebraically, i.e. the image here is algebraic. And then take that algebraic thing and really move it inside Z prime, signifying that it's actually the image of W prime inside Z prime.
So in our initial setup, the only thing that's not algebraic is Z prime, right?
Exactly.
Okay.
The only thing algebraic is Z prime, absolutely. And you have a map to it from an algebraic thing. We want to say that the image of the algebraic thing in the non-algebraic thing is still algebraic. Okay. So this is our lemma. So let me first explain before proving it how the lemma implies the theorem. So first, by step one, we can assume that phi is a modification. We can write S as U union Y, such that phi inverse U maps isomorphically U. Now, by induction, let's set Z to be the algebraic guy inside X, with the finalization as the pre-image of Y. So we have this breakup where we have Z inside X, Z is being contracted, everywhere else from Z we have an isomorphism. Now, by induction, the map from Z to Y can be algebraized. The definabilization of Z to Y. Excuse me. Now what we have to do is we have to algebraize the thickenings of Y, the thickenings of this map. Now note that Y sub k sits inside S, some infinitesimal thickening of Y inside S. And so this is a definable analytic space. And moreover, if I look at Y sub k inside Y sub k plus 1, then this is a square zero extension. There's the fact that if I take the kth power of an ideal and I square it, it's contained inside the k plus first power of an ideal, just because 2k is at least k plus 1. There's nothing subtle there. Okay, so now, applying the lemma to Z sitting inside Z2 and Z1, sorry, first thickening, and Y sitting inside Y1, we get an algebraic Y1 prime such that Y1 prime definabilized sits in Y1 and Z1 maps to Y1. So the first level we extend to the first neighborhood. We have our algebraic map from upstairs to downstairs, Z to Y. They both have thickenings. This one is definable, this one is algebraic. And the map extends to a map between thickenings. So it's exactly made for this lemma where we can sort of extend over one stage. And we don't algebraize the thickening, but we find something algebraic. We find something algebraic inside it, which we're calling Y1 prime, which is big enough to accommodate our image. And now continuing in this way, we apply the lemma to zk inside zk plus 1 and yk plus 1 prime, sorry, and yk prime, which we've already made by induction, sitting inside yk plus 1 to obtain yk plus 1 prime and zk plus 1. Repeatedly just go to a higher extension to get inside the full infinitesimal thickening these extensions, these Algebraizations. Now finally, we define y prime hat to be the limit of these y prime sub k's that we're making. So this is the formal neighborhood downstairs. X sub z upstairs maps y prime hat. This is our desired map on formal spaces, and now we apply our. Okay, so you have to be careful that like all the formal space stuff works out. There's a bunch of no-Euclideanity and regularity conditions you have to check. But this is the idea. Any questions about this stuff? Okay. If no, let me turn to the proof of this lemma, which is sort of the main step, how you extend these algebraic neighborhoods. Okay. So let me just start out by reminding everyone that W and W prime share the same point set, and Z prime share the same point set. What's different between them are the sheaves of rings on them, i.e. the functions we're allowing ourselves to consider in these two spaces. There's no extra points between them. So to record that, let's write down an exact sequence. So we have the following exact sequence on W prime. It's some sheaf of rings. You can, given a function on W prime, you can get a function on W just by forgetting the actual infinitesimal information that W prime records. And I is some ideal defining W inside W prime. Okay. And of course, if you want to, you can also definabilize everything and get the corresponding sequence of the definabilizations. Okay, now, given this, this sequence up top, what we can do is we can consider our map F and how it applies to the sequence. And so we get a corresponding long exact sequence if we take the push forwards along F. We'll call this map delta. Okay, so what is this sequence now? Well, this is now a sequence of sheaves on Z, because F is a map from W to Z. And these three things on Z are exactly what? So over an open set inside Z, which still does a risky topology, we're considering its pre-image in W, and we're taking all sections of our sheaves up and down. So basically, if you think algebraically, what this is over Z, for every open set in Z, this returns all holomorphic functions of the pre-image of that neighborhood in W. This does the same thing, but now we're allowing the extra infinitesimal information carried by W prime. The kernel is just those guys upstairs who are entirely in I, or in the kernel of the map, so that's not surprising. But push forward is left exact, it's not right exact, so there's no reason for this map to be surjective. Upstairs, it's a big open set, we have some function on it. There's no reason we can extend it to first order neighborhood over the entire neighborhood. This is kind of how, like, you can't always find a tangent field over an entire set, like over a sphere. This is very similar. Given the function, there's no reason to extend it. Unless your open set is something very small, which in this case it's not. Okay. And now here we have the theory of right-derived functors gives us this additional sheaf downstairs, the first derived push forward of I, and the co-kernel of this map, the failure of this map to be surjective, is measured by this delta. Okay, so this is something you can look at downstairs. I extract only this part of the sequence. Let me extend the diagram a little bit. So we have this map in the algebraic category. Let me now analytify everything. So I have the same map in the analytical category, not the definable category. I'm forgetting that for now. I'm only looking at the full holomorphic structure. Now I can extend it in the following way. So given an actual function on Z, a holomorphic function, I can pull it back to W. Given a holomorphic function on Z prime, I can pull it back to W prime. There's no reason for these to be isomorphisms, of course. I get way more functions upstairs that don't descend down, but I can look at these maps. Okay. Okay, and now in principle, having a map from W prime to Z prime can be recorded in this diagram. Because if we do have a map from Z prime to W prime, from W prime to Z prime, excuse me, and if I go up and right 2 steps, I have to end up being 0 in here. And that's the same as going right up right. And so I can measure whether this kind of map exists by measuring whether the image here and here lies inside the kernel of this map delta. So as I'm trying to construct this algebraic Z double prime, that's precisely the central property. Is can I find something algebraic which satisfies the property that boom, 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 I get 0. Okay. Now I want to point out, so note that these 3 sheaves, so F star OW, OZ, R1, F star I, they're all killed by I. And so these all, even though we're living on sort of W prime, these all exist on W. So all three of these on Z's, I'm sorry, we're downstairs. They all exist on Z, not on Z prime. So all three of these maps can be defined on Z. Okay. All three of these can be defined on Z. And so now we're going to use that to build our Z double prime. Maybe let me leave this up and I'll go over here. Right? So the way we're going to build this now is as follows. So we're going to define F to be the image of oh, sorry, give me 1 second. 1 second here. Sorry, give me 1 minute. Yeah, absolutely. Okay, sorry, I'm done. Let's call this map something. Let's call it psi. And we'll call F the image of psi inside this push forward over here. Okay. Now note, so the point is that Z prime is not algebraic yet, so we can't apply any of our algebraization theorems to Z prime. We want to apply things like definable Chow, definable Gaga, and various things already sitting inside algebraic coherent sheaves have to be algebraic, but in Z prime we can't do that. However, if we apply things to Z, then we very much can do that because that already has an algebraic stretch. And so the idea is we break up Z prime information into this map between two sheaves that exist on Z. And so because F star OW is already algebraic, so technically this is in the definabilization of this, but since F star OW is algebraic and coherent, everything here is coherent, it follows by definable Gaga that this capital F is also algebraic. Okay. This capital F is also algebraic. Now, finally, we have to define something algebraic to sit here, which will map to both of these spaces in such a way that the composition map is 0. So what we do is we define R to be the sheaf on Z, which is OZ direct sum over F star OW capital F. And so we just use this diagram forcibly to construct the sheaf, which is a square zero extension of OZ, which is algebraic because it's built from algebraic pieces sitting on set. We define Z double prime, the spec of R. So this is some sheaf in our definable analytic space. And we just say Z double prime to the definable analytic space, which is given by the same point set as Z, but by this extended ring of functions. Then by construction, it has maps here and here, which agree because you have projection maps to OZ and to F, which sits inside there, such that their composition to F star OW is the same. That's how this direct sum, that's what this sort of means. It means pairs of functions which map to the same thing. And so you can use that to construct this algebraic map of W prime to the space and show everything behaves to show. Okay. So that's a bit fast, I'm aware. But I hope this sort of idea of how the proof works carries through. Again, the idea is to take that infinitesimal information you don't have algebraic access to, record it just by looking at sheaves on Z through this extension map. And then once you have that, you can apply all the power of definable Gaga to Z and algebraize everything inside. Okay, so that's this. Let me think about next thing I want to start. So maybe this is a reasonable point to end. I'll just give a preview for next time. Even though we're a little bit under. So next time, I just want to mention the other kinds of functions that one can handle using this sort of approach. So next time we'll talk about derivatives of automorphic functions, and period integrals from a definable perspective. Essentially, once you have this technology, you can handle all the period integral functions in the way that we discussed from the perspective of local systems and definable structures on them. And we'll explain how this relates to differential Galois theory and some work at Bertrand, where he considers not just these functions, but also their derivatives with respect to algebraic differential forms in vector field on a base. But maybe because I'm low on time, I'll just stop here for now.
The next time is when?
Friday, I think. Yeah, I think that's our last lecture. Yeah. Yeah.
Is there any other
Yeah. Good question. Not so. There is an application to the mixed case as well. So we've been doing pure Hodge theory. You can do mixed Hodge theory, which basically means instead of considering smooth projective things and closed loops, you're allowed to study sort of indefinite partial integrals, not over closed loops, but between two different points or something. Or equivalently, you can study spaces that aren't smooth or aren't compact, just arbitrary spaces and integrals in those. But okay, that's very similar to this kind of thing. Beyond that, not really. There are no current other theorems. for the basic reason that I don't really know any definable analytic spaces that have algebraic information, like have maps from algebraic varieties, but aren't themselves already algebraic, right? You can sort of do Gaga type stuff and prove a bunch of stuff you expect to be is algebraic, but then this theorem is not really necessary because if everything's already algebraic, then who cares about your image? Everything in the world is algebraic. Hodge theory seems to be the one case that I'm aware of where you can find these kind of maps to a genuinely non-algebraic space, but from algebraic varieties. There's Simpson has a correspondence sort of higher Hodge theory where he considers higher dimensional local systems, and he looks at like moduli spaces of them, so like the Ram and Betty moduli spaces, and in principle something similar should hold in that framework. But those spaces are harder to study analytically, and so we've been unable to do a lot of things on them, provide a definable structure, show various maps are definable, understand them at all. So in principle, there are other kind of settings like Hodge theory where you have analytic parameterizations of things over algebraic bases, and a similar picture should hold, but we can't realize it. So at the moment, this is the only case I'm aware of. Yeah. All right. Thank you very much.